Okay, so this is for ketones and aldehydes part 2, problems 10 through 15. Okay, so the first one. Okay, so the following transformation is easily accomplished using a Wittig reaction. Show how you would use a Wittig reaction to do this. Well, you are converting a ketone to an alkene. The alkene portion has to come from a phosphorus ylide. So this is one way to make the ylide. Another way, you could just write triphenylphosphine, make that a plus, and CH2 minus. These are resonance structures, so that would be the Wittig. I will go ahead and show you the mechanism here. The ketone basically undergoes nucleophilic attack from the carbon anion, and what you get is a four-membered ring, cyclic ring, where you have oxygen and the carbon, CH2. This is still bonded to phosphorus, and now you just basically, these electrons from oxygen go towards phosphorus, and you make an oxaphosphatine. And it's just a four-membered ring. And then it collapses. The oxygen is going to go with the phosphorus, and those electrons are going to go to make the alkene. And this reaction works very nicely to give you an alkene from a ketone. Okay, the next one, number 11, show how you would accomplish the following synthesis. Benzene to N-butylbenzene. So let's draw we have benzene, and we want to go to N-butylbenzene. So just draw the benzene with 4 carbons, 1, 2, 3, 4, N-butylbenzene. And you can think of, well, would it be nice to do a Friedel-Crafts alkylation? But the problem with the Friedel-Crafts alkylation is you're going to get rearrangement, because that's really attaching a primary carbon. So the best way to do that is a Friedel-Crafts acylation. So we're going to just make an acid chloride and make sure we have 4 carbons, 1, 2, 3, 4. And then, so you have the acid chloride, and you also need aluminum trichloride to do the Friedel-Crafts acylation reaction. Now, that product is going to be carbonyl. 1, 2, 3, 4. So then the next thing you're going to have to do is a Clemmensen reduction, which is zinc with mercury and dilute HCl. And that will deoxygenate, so that carbonyl gets replaced with a methylene, CH2. Okay, so for B, benzene to para-methoxybenzaldehyde. So para-methoxybenzaldehyde. Okay, what you want to do is you'll want to do first a Friedel-Crafts, not Friedel-Crafts, just aluminum trichloride with chlorine. So you want to do a halogenation of benzene to give you the chlorobenzene. And I wouldn't want to do this reaction, but this is what we have to do because they told us to start from benzene. I would just start from a phenol, but apparently if you heat this thing with 350 degrees Celsius with sodium hydroxide, you're going to get an NAS chemistry. So basically the chlorine is deactivating enough for the ring. At high temperatures, that this will undergo nucleophilic aromatic substitution and replace the chlorine for an OH, which we call that a phenol. And then once you get the phenol, then the third thing you can do is react this. This is with iodomethane, the CH3 iodide. But first you're going to have to react the phenol with basically sodium hydroxide, and that will generate a sodium alkoxide, and then that undergoes an SN2 reaction with your alkyl halide to give you this methoxy group. Do you remember what that would be called? The Williamson ether synthesis. And then the last thing you would do, which I told you didn't have to know this reaction, is carbon monoxide, HCl, aluminum trichloride, and copper chloride. So there's a lot of reagents there. And that installs the aldehyde. Now for C. C, we have a phenyl. Let's draw the structure out. We have 4 methylenes, 1, 2, 3, 4, and then we have an OH here. And it wants to make the tetralone. And the tetralone structure is given to you. And this is going to be a Friedel-Crafts reaction. This will be an intramolecular Friedel-Crafts acylation. And so you can even count the carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So Friedel-Crafts acylation, what do you need? You need an acid chloride. So how do you make an acid chloride with a primary alcohol? You're going to have to first do the Jones reagent, which is Na2Cr2O7 and sulfuric acid. You can write it like that. Or you could just write H2Cr2O7. Either way, that's going to make that primary alcohol. It's going to oxidize it to a carboxylic acid. And then what do you do now that you have a carboxylic acid? 1, 2, 3, 4. 1, 2. You've got to make an acid chloride. Remember what reagent you use to make an acid chloride from a carboxylic acid? Thionyl chloride. Okay? And then, so Jones reagents 1, thionyl chlorides 2, and then we're just going to throw in some ACl3, aluminum trichloride, and that's going to do the Friedel-Crafts intramolecular cyclization to give you the tetralone. Okay, number 12. Show how you would synthesize 2 octanone from each compound. All right, so let's draw 2 octanone. That would be 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. And on number 2, you have a ketone. And then go back and count them. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So from heptanal. So we have 1, 2, 3, 4, 5, 6, 7. Heptanal. To go from heptanal, we need to add a methyl group. So we can do this using methyl magnesium bromide. That's a Grignard. So that's a plus and a minus. And then you have to add a little bit of acid to make the alcohol. And so that makes 1, 2, 3, 4, 5, 6, 7. And there's your CH3 that you added. But that makes a secondary alcohol. So then if you want to oxidize it to the product, you need to add PCC, pyridinium chlorochromate, and that will oxidize the secondary alcohol to the desired ketone. Okay, so that's A. Now for B, 1-octyne. So let's draw this out. I'm going to go ahead and draw the triple bond, because the YNE. I'll make that straight. So 1, 2, 3, 4, 5, 6, 7, 8. All right, so we don't need to add any more carbons because we got 8 in the desired product and we got 8 there. So we're not going to be adding carbons. We do want the ketone. Now, we have to go back to chapter 9 and do some thinking. There is one reagent that will give us a ketone with an alkyne through the enol polymerization, and the other one will give us the aldehyde. So you got to know the difference between the two. If you remember, it is, I want to say mercury sulfate and sulfuric acid. And that's going to give you the ketone. Okay? So that's chapter 9. Okay, number C, letter C, 1,3-dithiane. So what is 1,3-dithiane? This is 1,3-dithiane. You do need to know that. And now, what's nice about 1,3-dithiane, this carbon here between the sulfurs can get, it's like a masked carbonyl. Okay? It's a masked carbonyl. So we can make that a carbonyl. But now, what we need to be able to add to it, if you look at the desired compound, is we need to add a methyl on one side, and then we need to add 1, 2, 3, 4, 5, 6 carbons on the other. 1, 2, 3, 4, 5, 6. So how do you do that? Well, the first thing you do is you're going to add N-butyl lithium. N-butyl lithium is, in this case, a very strong base, and it's going to deprotonate one of the hydrogens on the 1,3-dithiane. So you're going to get this molecule here that's a carbon anion. Okay? Now you can react that with an alkyl halide and do an SN2 reaction. So the first thing you can do is react that with methyl bromide, and that's going to do an SN2, and now you have this compound here where you have still one hydrogen there, but you have a CH3. Now remember, I said that carbon is going to be your carbonyl, number 2 in your desired product. So then you're going to have to do the same thing again. So you're going to react it with N-butyl lithium, and that's going to generate the carbon anion. It's going to abstract that other proton here and generate the carbon anion. And then we're going to now react it with 6 carbons. We add 6 carbons. 1, 2, 3, 4, 5, 6, Br. 1, 2, 3, 4, 5, 6. So now this is going to do an SN2, and you are going to get CH3 here, and then CH2, and we want 1, 2, 3, 4, 5 CH3. So let's count that. 5, 6, 7, 8. We got 8 carbons. And then to cleave this is kind of like protecting group chemistry. The third step you're going to do is you're going to add mercury chloride salts, a little bit of acid and water. This is kind of like the acetal chemistry, because the sulfurs are very much like oxygen. They're below oxygen in the periodic table, and they behave like oxygen. So whenever you see sulfurs, you just think of them as bigger oxygens. So that's why this will cleave, and you throw in a little bit of mercury chloride, and it goes really fast. So that's going to cleave and give us our desired product. So there's our ketone. 1, 2, 3, 4, 5, 6, 7, 8. Because that will be a carbonyl. Okay, the next one is 2-octanol. So I'll just go ahead and write that. That one's going to be easy, right? So how do you make 2-octanol? From 2-octanol. That's an alcohol, secondary alcohol. Yes, PCC oxidation will take care of that. Okay, the next one, E, heptanoic acid. Heptanoic acid. So 1, 2, 3, 4, 5, 6, 7. Heptanoic acid. Well, you're going to need to add thionyl chloride. That's going to make the acid chloride. So go ahead and make the acid chloride. And then the second thing you're going to do is add a Grignard. So methyl Grignard. And you're going to quench that with a little bit of H3O+. And that's going to give you so this plus the Grignard attacks the carbonyl of the acid chloride. This kicks up. Chloride's a good leaving group, and now you have your desired product. All right, so our next one is 6-carbon cyano. 4, 5, 6 carbons, and then you have a cyano group. So 1, 2, 3, 4, 5, 6, 7 carbons. Well, you can hydrolyze a nitrile. So if you add H3O+ and water, you're going to make a carboxylic acid. So, and then once you make the carboxylic acid, do the same thing as you did up here, because now you got heptanoic acid. So you can react it with the thionyl chloride, make the acid chloride, and then react that with the Grignard. So you can do the exact same thing you did up here. And our last one is 2,3-dimethyl-2-nonene. See if I can remember that. 2,3-dimethyl-nonene. So 1, 2, 3, 4, 5, 6, 7, 7, 8, 9, 2, 3, 2, 3, 2,3-dimethyl-2-nonene. Okay, 2-nonene. Okay, so that should be right. 2,3-dimethyl-2-nonene. Well, do you notice that we have too many carbons? Our original product we need to make is 2-octanol. 8. So we want to make 2-octanol, we're going to have to do an oxidative cleavage. So we want to cleave this right here, this alkene. So we got to think about our alkene cleavage reactions, and then this is going to give us a ketone. So I would just add ozone. So you add ozone and DMS, dimethyl sulfide, to stop that, and you're going to get this octanone, and you're also going to get acetone from the other portion, from oxidative cleavage. All right, now we're on problem number 13. Show how you would synthesize octanol from each compound. The octanol, let's draw octanol. You have 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. And on carbon number 1, we have an aldehyde. This is octanol. And the aldehyde will always be on carbon number 1. Okay, so from 1 octanol. Are you thinking what I'm thinking? What reagent? PCC. Goes from a primary alcohol to an aldehyde. Okay, the other one nonene. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, if you cleave that with ozone and DMS, you're going to get the aldehyde. So that'll give you the aldehyde. So ozone and DMS. 1-octene. So that's the carbon triple bond, the YNE. So let's count 1, 2, 3, 4, 5, 6, 7, 8. And we want the aldehyde. So how do we go from an alkyne to an aldehyde? You remember SiA2 boron and then hydrogen peroxide with sodium hydroxide. That's that diisoamyl borane reagent, and that gives us an enol that does the tautomerization. And since it's a terminal alkyne, it's going to give us an aldehyde because the borane is going to add to the least substituted. That's the kind of the anti-Markovnikov. Okay, so that's C. Okay, D, 1,3-dithiene. Okay, so we have 1,3-dithienes. First, we got to draw 1,3-dithiene, and this is 1,3-dithiene. And it's kind of similar to what we did before. This carbon here between the sulfur is your aldehyde. It's your carbonyl. So we just need to add this portion, these many carbons. 1, 2, 3, 4, 5, 6, 7. We need to add 7 carbons. CH3, CH2. 1, 2, 3, 4, 5, 6, 7. And then that's going to be an SN2 alkyl halide. And so all we got to do is add in butyl lithium. That is going to deprotonate that acidic proton here to make a negative carbon, a carbon anion, with the N-butyl lithium. And then the second thing you do is you add this out, we're going to call that probably a bromoheptane. Bromoheptane. You call it 1-bromoheptane. It's going to do an SN2 reaction. And so then you're going to get 1, 2, 3, 4, 5, 6, 7. 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. And then the third thing you're going to have to do is cleave this. And remember I said that's kind of like that acid-tau chemistry, except we're going to add some mercury chloride in there. And then H3O plus and water. And that's going to cleave that and give you a carbonyl there. And that is going to be the desired product. 1, 2, 3, 4, 5, 6, 7, 8. And that's how you use 1,3-dithiene, because it is a masked carbonyl. Okay, the next one, 1-bromohexane. So let's draw 1-bromohexane. Well, you know what? That's what we did here, right? So, interesting. Let's see if we can overlap anything here. Actually, this is what you want to do here. Okay, so let's draw 1-bromohexane. 1, 2, 3, 4, 5, 6, bromo. Okay, so the first thing you want to do is just sodium cyanide, because you need to add another carbon. And plus minus. That's going to do an SN2 reaction. So 1, 2, 3, 4, 5, 6. And you have a nitrile. And the second thing you want to do, we haven't really talked about dibal yet. Diisopropyl diisopropyl, isobutyl aluminum. So dibal is abbreviated for aluminum hydride that has diisobutyl groups. 1, 2, 3, 4. So that's a diisobutyl. And if you think about it, so you have, you've seen lithium aluminum hydride. That's a pretty hot reducing reagent. That aluminum has 4 hydrides to deliver. Dibal is just the reduced reactivity. So if you substitute those hydrides for this organic compound, then you reduce, it's milder. So this is very mild. And you can reduce and add a little bit of acid, because you always need to add a little bit of acid to quench the aluminum. That will convert a nitrile to an aldehyde. And that's an important reaction that we're going to definitely talk about tomorrow. 1, 2, 3, 4, 5, 6, 7. And is that what we needed? For some reason, I'm wondering if I have enough carbons there. I think we'll just go on. Okay, and then our last one, we have octanoic acid. Octanoic acid. Octanoic acid, basically you use lithium aluminum hydride. This is what you're used to seeing, and that will reduce the it will reduce an acid, a carboxylic acid, to the alcohol. And then you can, so one, 2, 3, 4, 5, 6, 7, 8. So that goes to the primary alcohol, and then you can just PCC oxidation to give you your aldehyde. Okay, number 14. Show what the products would be via oxymercuration of the following alkynes. Okay, so this is chapter 9, oxymercuration. So let's do 1, 2, 3, 4, 5, 6. This should be a straight linear. Okay, so that's A. This is important just because it makes ketones and aldehydes. So oxymercuration is mercury sulfate and H2SO4 of a triple bond. You're basically getting a ketone. 1, 2, 3, 4, 5, 6. It doesn't matter, they're both the same. Okay, so for B, 1-hexyne. Now you're going to have a little bit more stereochemistry here, regiochemistry. 3, 4, 5, 6. And so when you add the mercury sulfate and sulfuric acid, you're going to get the ketone on the internal carbon. So you get CH3 carbonyl, and just add your carbon chain. On C, you got cyclodecine. Okay, let me tell you, when you're drawing these 10-member rings, draw them like this, like you're going to close it up, and then draw another one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then draw your triple bond there. And same thing as you had from the very top. Just try to redraw this and basically put a ketone there. And you can pick one or the other. Either one of those will work. Regiochemistry won't matter. And last but not least, these nice little structures A through K. So let's see what we can do here. Okay, so A, structure A. So when you do this and you work it and you want to see, where I have my structure A. A is 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. So let's look at this. 7. How would you know that? Okay. Well, you want to start, let's start with this one here. This 1,3-dithiene. Okay, so with N-butyl lithium, you're going to generate this. You're going to generate your carbon anion with N-butyl lithium. And then it says react it with D. Well, D needs to be a, well, this CH3 is going to be this CH3. And this carbon here is going to be this carbon. So D is going to be 1, 2, 3, 4, 5. 2, 3, 4, 5 alkyl halide. And so that's going to do an SN2. And then that's going to give you structure E. So this is structure D. Structure E is going to look like this with the dithiene. CH3, and then 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, so that's structure E. And then with mercury and mercury and acid, you get structure A. Another way to find structure A would be from the 1-heptine. So what does 1-heptine look like? Let's draw that. 1, 2, 3, 4, 5, 6, 7. And then F. What is F? F has to be mercury, sulfate, and sulfuric acid, because you have an alkyne and you're going to make a ketone, which is A. Okay, G, look at the reagents for G. That's ozone and DMS. So you're doing ozonolysis. So when you do an ozonolysis and you want to make a ketone, A is your ketone. What's your structure for G? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Where your ketone is, you better have a double bond there to cleave. So you could just, that could be your structure for G. And I'm going to double check to make sure, yes, so that's G. So that's just the CH2. Okay, because that's going to be ozonolysis. Okay, let's go over here. We have the Grignard with B to make C. So what is B? B should be CH3. So it's just acetyl aldehyde. And the reason why is because you want your Grignard to do a nucleophilic addition. And that's with acid, it's going to give you the alcohol. So that is going to look like, let's draw that structure out. You got 4 or 5 carbons, 1, 2, 3, 4, 5 carbons. And then you've got the COH, CH3 from your Grignard. And now you've got, that's C, structure C. And now you've got Jones reagent, or it could be PCC, that oxidizes that secondary alcohol to the aldehyde, or in that case, the ketone. Now, okay, that takes care of the top. Now let's look at the bottom. Okay, so we have the aldehyde, and we're going to react it with HCN. So what does that look like? Well, you take A, 1, 2, 3, 4, 5, and you react it with HCN. So that's basically cyanohydrin. You're going to make a cyanohydrin. So there's CN and that's the OH. And we've talked about cyanohydrins. So that's the structure for H, the cyanohydrin. And then with acid, you're going to make structure I. Did I put structure I on there? Thinking out loud here. Well, what happens when you do the hydrolysis of that? I want to say you're going to make a carboxylic acid. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, and you'll make a carboxylic acid from that nitrile. Okay, and I will double check that one. Now, what about J? What is J? J is phenyl magnesium bromide, because you see the phenyl's added right here. So you're going to add a phenyl and make a tertiary alcohol. So you know that you can do phenyl magnesium bromide and do a Grignard to a ketone with a little bit of acid and make a tertiary alcohol. That's how you make that. And then K, you are adding another Grignard. So let's draw A. That's what you're reacting it with. And you're going to react this with this Grignard here. And it is an acetal protected Grignard, and the acid's also going to cleave that. So let's just look at what that does. Plus, minus, and makes the alcohol there. So you can see this portion is your alcohol. It makes a tertiary alcohol, but the acid's also going to cleave this acetal group. And that acetal, which you all learned that new functionality, is a ketone to give you your desired ketone.